Hello guys, it's Dr. AJ. So today we're going to solve examples on stability of retaining structures. This topic basically is very important. You're always going to get questions on them in the PE and the FE exam. So let's get started. So example 1, as you can see, we have 15-foot tall retaining wall at rest condition. So this is a keyword. The density is given, angle of internal friction phi is given, and OCR is given. OCR is over consolidation ratio. This is another keyword. So we have two keywords here: rest condition and OCR, please. And it is required to find the force applied on that wall. As usual, we write down what's given: gamma sand, phi, OCR, H, and at rest condition. So the soil will apply stresses on the wall, and stresses, it looks like a triangle, or let's say has a triangular profile. And from stresses we can find the force, as you can see here, the black one. So as you go deeper and deeper, we are getting more stresses and higher stresses applying on the wall, and we're gonna go over that in a minute. So first thing first, we go to the reference manual and we find the K naught. What's the K naught? Here are the K naught. Since we are dealing with rest condition, K naught here, it's at rest earth pressure coefficient. Please pay attention. This is, since we have at rest, we're going to be using K naught. We're not going to be using K sub A or K sub P. Those basically for active cases, for active forces. If the question, by the way, if the question did not tell you what type of condition you have, by default you're going to be using active, the K sub A. So please, it is not K sub A, not K sub P. That's very important. Now, since we know it's at rest condition, we're going to be using K sub naught. We go here and decide. We have two equations, one for over consolidated soil and the second one for normally consolidated soil. And since we have OCR, over consolidation ratio, we're going to be using the green one, the one with the OCR. And those basically, this and this and this is just, and all three parts, 1, 2, 3, in the same page in your reference manual. We write down the equation, 1 minus sine phi, OCR to the sine phi. Sine phi is given 30, sine phi is half, so we know that. OCR is 1.5. So we just plug in the numbers, we do a little bit of mathematics, and we're going to get K naught of 0.612. So what is K naught in general? K naught is a coefficient that converts the vertical stresses to horizontal stresses. So gamma H, it's a vertical stress. You multiply it by K naught, it becomes a horizontal stress. So we go now and find the vertical stress. What vertical stress is basically density times depth, right? The density, please pay attention. Always, always, always use effective density, not the total. But since we don't have water here, the total is the same as the effective. But if you have a groundwater, you have to use the effective, because this is the one that works with K naught, with the coefficient factor. K naught will not be applied to the pore water pressure, will not be applied to the effect that comes from the water. So this is very important, because the water always, whether it is gamma water times depth, that's the vertical, and the horizontal is the same as well. So it doesn't mean if you have water you're not going to calculate it. No, you will calculate it, but K naught will not, or Ka or Kp will not be multiplied with the water thing. That's why we use it effective always. So as you can see here, gamma effective equal gamma total. So we're good to go. The density, we have 120, it's given. 15 is the height of the wall, and that's going to give us 1800 psf vertical stress. Now we have the K naught, the sigma v. We multiply those guys, we're going to get the horizontal stress, 0.612 from here to the K, 1800 the vertical, so that's going to give us 1100, 1.6 psf horizontal stress. This is basically here. So now we need to find the force. The force is basically, since we have a triangular profile of stresses, so in order to find the force, is just the area. What area? The area of triangle. Sigma h, which is k naught gamma h, or k naught times the sigma v. This is the length or the width of the triangle, and the 15 is basically the height. And then we apply the area of triangle equation, half sigma h times h. We just found that this is given, and that's going to give us 8,262 pound. Because it is pound. If you do the math, this is pound per foot squared, and this is foot. So we should be getting here pound per foot, right? That's normal. But since it's per unit length, it'll become pound per foot times 1 foot, so it'll become just pound. That's why we just put pound here, because it's per unit length, and that's approximately 8.3 kips. So from the options, it is D. With that, thank you very much and see you next time.